Welcome to Shanti-Peace for Mathematics. In this video, we are talking about the conformal mapping. This mapping plays an important role in study of the various physical phenomena defined over the given domain and the curve of arbitrary shapes. It's majorly used in the field of fluid dynamics or fluid mechanics, where the two fluids are crossing to each other, and when what is the situation, which transformation you apply on it, so that angle will preserve to that. So the conformal mapping in some sense is also known as the angle preserving map. So before going to this angle preserving map or a conformal mapping, we need to understand what do you mean by angle of rotation. So let us say this gamma is equal to z of t is a smooth curve. Now what do you mean by a smooth curve? It means that this gamma equal to z of t is a differentiable function. Smooth curve means the function is differentiable everywhere in its domain, and it is a complex function, so that's why I am just taking z of t is equal to x of t plus I y of t. This is given to you, where the domain of this t function, t variable, will be between a and b. Z of t is a smooth function. That means its first order derivatives are exist and they are continuous. That means x dash of t and y dash of t are exist in its domain, that is the domain between a to b, and they are continuous also. So these two functions are continuous, and the derivative of this we can write as x dash of t plus I y dash of t. That is the derivative of the real part and the imaginary part. This is, we can say, for every t which is in the open interval ab. It is to be noted that the increasing value of this parameter x will gives you a positive direction, and if it parameter x will be decreasing, then we are going towards the negative direction. Now let us say f of z is a function which is defined on this gamma curve, and w equal to f of z equal to f of z of t, where t is between these two. Now suppose that gamma passes through the point z0. Let us try to draw the figure of this situation. So if you can have, this is your y-axis and this will be your x-axis, and if there is a curve, the gamma curve, and there is a point z0 is there, it's passing through this z0 point that I have written exactly. And what we are assuming other things is f is an analytic function at the point, f is analytic at the point z0. Then by chain rule, what we can say, as you have the previously, it is w of, we can write as f of z, which is as a function of t, so that's why it is f of z of t. So at the point t0, what is w dash of t0? By chain rule, what we can say, it is this is equal to f dash of z of t0 into z dash of t0, where t0 is between ab. And what is this? z0 is exactly z of t0. So now, if this f dash of z of t0 is non-zero, so that is the requirement we are taking, that we are assuming that this derivative is non-zero, and also we are taking this smooth curve, it is not the straight line, so that's why I am also taking that f dash of t is equal to this is also non-zero. So that means this is non-zero and this will be non-zero. That means this is a non-zero number, so I can have its argument. its amplitude we have. So if you apply the amplitude both sides, then it will be having by argument formula. As you know that the argument of Z1 into Z2 will be argument of Z1 plus argument of Z2, argument of f dash of Z of T0 plus argument of Z dash of T0. Now what is Z dash of T0? As you know that it is the argument is nothing but the slope of that, of its tangent. So this is actually a slope of the tangent at the point Z0 of the gamma curve. So that is this thing we have. This is the tangent and its argument, that means what is that angle making with the positive x-axis. So this is your argument and I am denoting as a theta. On the other side, what will be this? This will be the image of the function, that is the w is equal to f of z is there. So this gamma function, it is in z plane. So that z, whatever the function is there, that transformed into the w plane. So if it is transformed to the w, let us try to draw a same concept. Let's say this is your y-axis and this will be your x-axis and this will be your v-axis and this will be your w. Your x-axis, this will be y, this is v and this is u-axis. This is your xy plane or z plane I can say, and this is v plane or w plane. Now this is your gamma curve in z plane. There is a point z0 here. This z0 making the angle or a slope of this line at this point will be theta that we have measured. That is the argument of z dash of T0 that we have. Now as I am discussing that the image of this gamma function under the transformation w is equal to f of z is some another function into the w plane. So image of that plane under this transformation is this. Now the image of the z0 point is actually a w0 point that you have. Now the angle of the tangent at this w0, so this is the tangent there, and the angle of this tangent or slope of this tangent we denote it as phi of z0, and that is nothing but the argument of f dash of z0. Hence, as we have discussed above, that is the argument of w dash t0 equal to argument of f dash of z0 plus argument of z dash of t0. So therefore this is not, what is this? This is the phi of the thing that we have assumed, phi of 0 or phi. This will be denoted as xi of 0 and this will be theta that I am just re-denoted as theta 0. So this is theta 0. So this theta 0 is makes the angle inclined with the direction to the tangent to the gamma. The value of argument of z dash of t0 is also phi of t0, and in inclined direction to tangent, the image of that gamma will denoted as capital gamma, which is, I can say, it is the image curve, whereas the rotation of this gamma is the value of this argument of f dash of z of at 0. That means this much rotation, that much difference you will have found. This z0 is nothing but the phi of 0 minus theta 0. So whatever the angle of difference is there, that much rotation is happen when you apply the function w is equal to f of z onto this gamma function. So that is the meaning of angle of rotation. Now let us see this concept with the help of an example also. So let us take this example. Verify by taking some particular curves the angle of rotation under the transformation w equal to z square at the point plus I. So verify by taking some of the particular curves. Here the given function is w is equal to z square, and we need to find out the angle of rotation at the point 2 plus I. So what is the argument of f dash of 2 plus I? Because argument of w dash of t0, which is equal to argument of f dash of z of t0 plus argument of z dash of t0. So this much argument is there, which is the rotation, angle of rotation. That is our objective, is to calculate and verify. So let us try to calculate what is the first thing is what is this quantity, the argument of f of this one. So that is nothing but the image of this point, that is w is equal to z square. So the derivative of this, the f of z is z square. So derivative will be 2z, and at the point 2 plus I, this will be 2 into 2 plus I, so that will be 4 plus 2i. And so I can write this is nothing but the argument of 4 plus 2i, and you know that by using the tan inverse, this is tan inverse of y by x, so it is 2 by 4 plus 2 and pi, where n belongs to z. So this is finally you will have tan inverse of 1 by 2 plus 2 and pi, n belongs to. So that is on the one side, that is this. We need to prove that this minus this is exactly this one. So here the question was by taking some particular curves. So I need to take some particular curves here. So let us assume one curve which is passing through this point. That the curve, you can take any curve. Let us consider the curve y is equal to x minus 1, and it is passing through the point 2 plus I. You can check by substituting the value here. So what is your z of t? Z of t is x of t plus I y of t as per the definition, and I am taking here t will be minus infinity to plus. If z of t is t, then y of t according to that it is t minus 1. Now what is z dash of t? Z dash of t is 1 plus I into 1. Now the argument of z dash of t is tan inverse of 1 by 1. So that is tan inverse of 1. So that's why it is pi by 4. Why we have calculated? Because here we need to calculate that quantity at the point t0. t0 is 2 plus I. So we have calculated this side quantity is pi by 4. Now we are calculating this side quantity, which is the image of, which is the angle of the tangent of the image curve. So first of all, I need to find out what will be the image curve of that of t. That means what is the image of this line, w equal to z square under this map. We can have, if I substitute as w as u plus iv and xy as x plus iy, and if you simplify both sides, you will have u equal to x square minus y square, and v will be 2xy. Now we just substitute the value y is equal to x minus 1 into here. So what we have, we will get u equal to x square minus 1, x minus 1 also. That will give you x plus 1 into x minus plus x minus 1 by making a square minus b square, which is a minus b, a plus b. By using this quantity, we got this. Now this x is cancelled out. So finally you will have u equal to 2x minus 1. So that's why x will be u plus 1 by 2 that we got. And by putting the value of x into the here, you will have value of y. will have y is equal to x minus 1 and you will get x is equal to plus 1 by 2. Let us check whether you have this. Yes. Now by putting the value, that is u plus 1 by 2 minus 1, that will give you u minus 1 by 2. So you have the value of x and value of y. So therefore you have v, which is 2xy. Now substituting this value here, that is u plus 1 by 2 into u minus 1 by 2. Just check, u is cancel out. You will have this is u square minus 1 by 2. So finally you will have the equation which is v is equal to u square minus 1 by 2, which is the gamma curve. Because this curve does not involve any terms of x and y. So this is the image of the line y is equal to x minus 1. This is the small gamma curve and this is the image curve, what we can say. Now here the point is, here the image is 2 plus I. So what will be the image of 2 plus I under this map w is equal to z square. So let us making the square, that is z square is a function, w equal to z square is a function. I am just substituting that value here. So it will be 4 minus 1 plus 2 I into 2. So this is 3 plus 4i. That will be the image of the point 2 plus I. So I need to calculate what will be the slope of this curve at this point. So how to calculate the slope of any curve at a given point? By taking its derivative. So I am just taking the derivative of this equation, that is v by du will be u, and at the point comma 4, that is 3 plus 4i, we have the value u, so that is 3. Hence the angle you have, the tangent is tan theta. Here we have denoted as phi. So tan phi is equal to 3, that is the final dy by dx you have. So phi will be tan inverse of 3. Now the angle of rotation phi minus theta. What is the value of phi? We have calculated is tan inverse of 3 minus phi by 4. That is nothing but the tan inverse of 3 minus tan inverse of 1. Phi by 4 we have calculated above, that is here, you can see that. And by putting that value of phi by 4, that is tan inverse of 1, and applying the formula tan inverse of x minus tan inverse of y equal to tan inverse of x minus y upon tan inverse of x plus xy. Using that, this is tan inverse of 3 minus 1 upon 1 plus 3 into y is 3. So this is tan inverse of 2 by 4, and which is exactly tan inverse of 1 by 2, which we got the value of xi. So that we have obtained here tan inverse of 1 by 2, which is the angle of rotation, which is the argument of f dash of 2 plus I. So let's verify this example, that is the angle of rotation. So ultimately the angle of rotation will be, you can calculate the angle of rotation, that is argument of f dash of z0, that is equal to argument of z0, which is of minus sign, plus argument of w dash e0. So ultimately this is the subtraction of the two angles, how much angle of rotation is happened after applying the function. Now let us go to the definition of the conformal mapping, or I can say angle preserving map. So a mapping f of z is said to be an angle preserving map or conformal at point z0 if it preserves the angle between oriented curve passing through z0, magnitude and sense. Sense means the direction. So if you have the conformal means it's preserving the angle between the two curves in the form of a magnitude as well as in the sense. Let's see by a figure geometrically how this is the things is look like. So if you consider this is your x-axis, this will be your y-axis, this is your u-axis, and this will be v-axis. This is your z plane, and this will be your w plane or uv plane, whatever the name you want to say. Here there is a two curves. Let's say that two curves are gamma 1 and another curve I may draw like this. Let's say this is the curve gamma 2. So there will be two curves are there, gamma 1 and gamma 2. Now image of this curves under the transformation w is equal to f of z is the gamma 1, this is bigger gamma 1 and another curve is gamma 2. So the image of the gamma 1 is this capital gamma 1, image of gamma 2 is capital. Now let us try to draw and tangent to both these curves. Gamma 1, this is the tangent to the gamma 2 and this will be the tangent to the gamma 1. Here is also I am drawing the tangent with respect to gamma 1 and the gamma 2. I also forgot to mention that this is the point z0 and the image of that z0 is w0. Now if the angle between these two curves, how to measure the angle between these two curves? That is nothing but the angle between their tangents is theta, let's say, then the angle between these two curves is also theta. Now in the sense means it is in the terms of the direction, that means the orientation is the same as well as the magnitude is also same. If such type of situation occur, then we can say that the function f is conformal at the point z0. So this is the definition of the conformal mapping, or I can say it is a angle preserving map. So that's why it is angle preserving. So here whatever the angle is there, the same angle is preserved by this function. If the angle is preserved, we can say it is angle preserving map or it is conformal map at the point z0. Now if you want to say a function f is conformal on D, if it is a conformal at every point of its domain. So that's why the definition of conformality on the domain is defined. Conformal domain is nothing but it is conformal at every point in the domain. Now to find out this whether the given function f of z is a conformal or not, it is difficult task to deal with, because when you given a two curves, first of all you have to find out the tangents, the slope of the tangents, and then you need to calculate its angle between them. Also you have to go with image of that, and also you have to do the same procedure over there. But is there any shortcuts or any theorem which based on that you can say that if this condition is satisfied, then we can say it is a conformal. So for that we have the next result. It's also known as the conformality theorem. So this theorem states that the transformation is affected by analytic function w equal to f of z is conformal at every point z whenever f dash of z is non-zero. So affected by analytic function, that means the function has to be analytic. If you want to say that this function is analytic, its first order derivative should be non-zero. If first order derivative is non-zero, then we can say that it is the conformal mapping. Let us try to give the proof for that. Okay, so here what I am taking again, let us consider this is your x-axis, this will be your y-axis, this is u-axis, and this will be v-axis. Let us consider the p of z is a point in the region of z plane. The image of this point is P dash of W. This is P of Z, the image of is P dash of W, and corresponding to the point it is in this is W plane, and this will be your Z plane. Now suppose that Z moving along the curve gamma, there is one curve gamma, let's consider this is your gamma curve, and this P dash is moving along the curve, let's say that is a capital gamma. So image of this gamma is this under the transformation W is equal to F of Z. Now I am taking another point, that is this point Q of Z plus delta Z, which is the point is the neighboring point of this P of Z onto the gamma. Here we will have the image of this Q of Z plus delta Z will be Q of W plus delta W, which is the image of this will be denoted by Q dash. So from this what we get is PQ, that is the vector which is delta Z, and P dash Q dash which we have delta W, that we can see here, that is this vector. If you consider, then this is delta Z, the length of this vector, and this vector is delta W, where the delta Z and delta W are the complex. I am assuming that the modulus of this delta Z is R, and the argument of delta Z is theta. This is we assume. So if it is there, then we can say that delta Z will be R e power I theta, because now it is a complex number, so it can be represented in this manner. For W, I may write down as delta W modulus will be R dash, and the argument of delta W I may write as theta dash. So that means this delta W I may write as R dash e power I theta dash. Now let's do this, delta W upon delta Z. So as per this will be R dash upon R into e power theta dash minus theta. That is the quantity you will have. What will take now? We'll take this delta Z tends to 0. What will happen if the delta Z tends to 0? A tangent at P. So let us try to draw a tangent at P. Make the angle with the positive x axis as a theta. And tangent at P dash, that will be this, which makes the angle with the positive u axis. Theta I have already used, so that's why I am using here it is alpha, and this will be alpha dash. So what will happen if I consider the delta Z tends to 0? The delta Z tends to 0, then this point is approaching to this, it's going towards this point. So hence, what will happen to this alpha angle, this theta, the angle right now, angle between this and this is theta. So that means if delta Z tends to 0, the theta will approaching to alpha. And here what will happen to W, so this is your theta dash, and theta dash will goes approaching to delta dash, because if this point is moving towards this point, the image is also having the same thing, so that is also moving towards that side, and hence if delta Z tends to 0, we have theta is tends to alpha and theta dash is tending to alpha. So now I am taking the limit here, that is limit delta Z tends to 0, delta W upon delta Z will be limit. Here delta Z is not there, so that's why I am just using theta comma theta dash, which tends to alpha comma alpha dash R dash upon R into e power I theta dash. You don't know whether this R dash upon R is a function of alpha is there or not, so that's why for that I just write down this quantity as it is. So r dash upon r, and I am applying this limit to this quantity, so that is e power r dash minus alpha. That is the things you have. And what is this side? You just observe this one is nothing but the derivative, that is f dash of z. And if I assume this f dash of z is rho e power I phi, and if you compare this real and imaginary part here, you will have phi is equal to limit of theta dash tends to alpha dash r dash upon r, and phi will be alpha dash minus alpha. So this is the relation we got. We call it as the equation star. This quantity we have did for only one curve. Let us consider there is another curve gamma 1 which is passing through the point P. So what? Let us try to draw that figure again. So let us have, this is your x axis, this will be your y axis, this is your u axis, and this will be your v axis. There is a point. If P is there, we have already considered the one curve gamma which is passing through this point, and all this calculation above we got for gamma. There is another curve is gamma dash that we are assuming, which is passing through the point P. The image of gamma that we have considered as this gamma, and there is the point P dash which is the image of this P point which is here, and there is another curve which is the gamma dash. Let's say this is look like this, which is passing through this point P dash, and this is the image of this gamma dash. Now, as we have discussed the same calculation for gamma and its image, true for gamma dash and its image gamma dash, capital gamma dash. So what we have, if you can have the angle with positive x axis, suppose let's make the angle with the positive x axis as alpha, if this is the tangent to that. So this is, we assuming it is a beta angle is making. So its image here, it makes the angle beta with positive u axis, which is beta dash. Then as we have the same argument did here, we can write it is rho equal to limit theta dash tends to beta dash r dash upon r angle phi, which is the angle between the two curves, that is angle of rotation between these two curves beta. Since the angle of rotation is the same, and if I call it this is the double star, since angle of rotation between these two curves will be the same, we can write that alpha dash minus alpha equal to beta dash minus beta. So hence, what is alpha and what is alpha dash minus beta? Let us see in the figure. So this is your beta, and let us try to draw what is the alpha in the angle of tangent. Here what is gamma, bigger gamma dash, which is there. Now angle between this, that is beta dash minus alpha, which is this one, beta minus alpha, which is this angle, and here angle between these two is beta dash. So it is, hence you will have the
beta minus alpha is same as beta dash minus alpha dash, and hence this angles are preserved. So we have proved that if the derivative is non-zero, then the angle is preserved by this transformation if it is analytic. Now the question is, where we have used this condition f dash of z is non-zero into the proof of this theorem. That is, I am giving you as an exercise to find out where we have used this condition while proving this theorem. Let's have, that is the next theorem, which states that let f be a analytic at z0, f be a conformal at z0, then there exists a neighborhood of z0, let's say that neighborhood is n, such that f is conformal on n. Means that f is analytic and it is conformal at one point, then there are infinitely many points on which the function is conformal. In the previous statement, we have proved that if f is conformal plus analytic at the point z0, then it will imply that f dash of z0 is non-zero. And also we have proved one of the results in my previous one of the video, in which we have seen that, let's say that results will state again here. So let g be a continuous function at point z0 and g of z0 is non-zero. Then we have proved that there exists a neighborhood of z0, let's say that neighborhood is n, such that g of z is non-zero for every z in n. Now this result we have already discussed in my previous one of the video. The link you can find out from here. Now due to this result, what we can say about this, we have the f is conformal, and which implies that f dash of z is non-zero. Now if you apply this just by replacing g by f dash, you will get our result, because now if f is analytic, so therefore it is also, its derivative is continuous. So we can say that f dash is continuous and it is non-zero due to its conformality at the point z0, and that's why you will have, there exists some neighborhood of z0 such that f dash of z is non-zero for every z in that neighborhood, and hence we can say that f is conformal on the n. Here also I want to mention one of the very important thing is f is conformal at the point z0 if and only if I can say that f dash of z0 is non-zero. In the book of Brown Churchill, they have defined this as a definition. This is they stated as a definition of conformal mapping, and then they are proving using this definition, they will prove that the f is angle preserving also. So in some of the book they are making this as a definition, and then from that they are trying to prove that the function is angle preserving map. So this is just a note that I want to say to you. Try to discuss some examples. So the question is, discuss the conformality of the function f of z is equal to e power z. So as you know that the derivative of this function is itself, and e power z is never 0 for any z belongs to C. So we can say that f is conformal at every z which is in C. So it is conformal in entire plane. Let's say another example. Let us discuss the conformality of the function z square minus 2z plus 1. So f dash of z not equal to 0 implies that 2z minus 2 is not equal to 0. That will imply z is equal to 1. Z is not equal to 1. So hence the z is not equal to 1. So all those points where z is not equal to 1, where the function is conformal. Now next concept that here we need to discuss is about the scaling factor. See, what we have discussed is about the function w is equal to f of z is the angle preserving map. It is a conformal map at the point z0. Suppose we are considering the function which is a conformal at the point z0. That means the function is, its orientation is the same, but function may behave, its scaling will be there. So what is the quantity on which the function scaling is possible? So for that, what I can do is f dash of z0, if I have that, we can by definition will say it is limit of z minus z0 mode of f of z minus f of z0 upon z minus z0 is there. Now equivalently we can say that this is nothing but the f of z minus f of z0 upon z minus z0 is there. So it presents that this will represent that if f dash of z, or I can say f dash of z0 is greater than 1, then there is an expansion is there. So here is the expansion of the figure in its image you will have. If we have the f of z0 is less than 1, then it is a contraction. If f dash of z is equal to 1, then there will be no movement will be there. The expression of argument of f dash of z is depends on the how much rotation is there, and the factor, that is f dash of the z, which is a modulus of that, which is known as a scaling factor or scale factor. It is follows by conformality in this value approximating the argument of z and modulus of f of z0 at all the point nearer to z0. It means that the image of a small region in the neighborhood of z0 conforms to original region in the sense that they are approximately the same shape, and the large region may be, however, the transform into the region that bears the resemble with the original value. For example, if you consider the function f of z is equal to z square at the point 2 plus I. So at this point, this function f of z is equal to z square is conformal because its derivative is 2z, and which is non-zero. Angle will be the same of the image, but what will be the scaling factor? How much scale the image will be there? So to calculate that one, let us calculate what is f dash of 2 plus I. So f dash of mod of f dash of 2 plus I is a 2 into 2 plus I, which is nothing but the 4 plus 2i, and hence this will be square root of 16 plus 4, which is square root of 20. So this much scaling of the curve, it is in z plane, and if you transform that curve into the w plane at this point, will be the scaling will be this much. So it will increase. The scaling is there, or it is, I can say it is an expansion is there. If this value is bigger than 1, then it is expansion. If this value is less than 1, then it is a contraction. If it is equal to 1, then there is a no scale. So in that manner, you can just say it is a conformality related to it. So let's have the now next example. Verify conformality at a point z is equal to 1 without using the above theorem or the map w equal to 1 upon z. So here we need to verify the conformal theorem or conformality theorem that z is equal to 1 will be there. So I need to choose two curves which are passing through z is equal to 1. So by simple curve, if I take as y equal to 0 and y equal to x minus 1. I will take these two curves which are passing through z is equal to 1 point. Now let us try to find out what is the image of y equal to 1. So first of all, I need to have what is the real and imaginary part of this function in terms of y. So since you have z is w equal to 1 upon z, we can write this as z is equal to 1 upon w. So that will be 1 upon u plus iv. And hence this is 1 u minus I upon u square plus v square by multiplying its conjugate. So therefore x, if I consider this is as x plus iy, so this will gives you x is equal to u upon u square plus v square, and y will be minus v upon u square plus v square. So therefore y equal to 0 will implies minus v upon u square plus v square will be is 0 will be v equal to 0. So this is the first gamma curve is there, or I can say image curve is there. The second one we have it is y equal to x minus 1. So if I substitute the value of x and y here, we'll have minus v upon u square plus v square equal to u upon u square plus v square minus 1. So if you simplify this, this is minus v equal to u minus of u square plus v square. So hence this will gives you u square plus v square minus u minus v equal to 0. This is another curve is the gamma dash curve. So this is your gamma curve, first one, and this is gamma dash curve, and its images are this, and this will represent the circle. This will represent the line that you know, which is the u-axis. So let us consider this is your x-axis, this will be your y-axis, this is u-axis, and this will be your v-axis. Now we need to plot this curves. These are the two lines we have. This will be the line which we have y equal to 0, which we have here, and this is the line. For that I need to plot 2 points, that is, if x is 0 then y will be minus 1, and if y will be 0 then your x will be 1. So that's why we need to plot these 2 points here. So this is the point 1 comma 0 if you consider, and this is the point somewhere here, it is 0 comma minus 1, and you have a line joining by these 2 points which is like this. This will be your line, that is y equal to x minus 1, and this is the line y equal to 0. The angle between them, that you can just note that, and the point is given you is z is equal to 1. The angle between them, it is pi by 4. How you can conclude it is pi by 4 is just by taking, so it is then just a slope of the line is there. So if I compare that line with the ax plus by plus c equal to 0, so then we will have the equation is of the form x minus y minus 1 equal to 0. So your a will be 1 here and b is minus 1. So the slope will be tan inverse of, or the angle with the positive x-axis is nothing but the tan inverse of b by a, which is tan inverse of 1 by 1 because b is minus 1. So that's why it is 1 by 1. So it will be pi by 4. So the angle between these two line is pi by 4 that we have concluded here. Now here on the other side, the image of this line in the UV plane, you have v equal to 0 that we have concluded. So v equal to 0 line is this, which is the u-axis. And what is this represent? As I already mentioned you that this is the circle, but let us try to conclude what is this circle is. So it is u square plus v square minus u minus v equal to 0. So hence this is u square plus v square plus 2gu plus 2fv plus c equal to 0. If you compare this equation with this, you will have 2g is equal to minus 1 and 2f is minus 1 and c will be 0. So your g is minus 1 by 2, f is minus 1 by 2 and c is 0. So you just you know that this equation represents the circle if g square plus f square minus c is greater than 0. So let us calculate this quantity. This quantity is 1 by 4 plus 1 by 4 minus 0. So that is 2 by 4, which will be 1 by 2 and which is always greater than 0. So that's why this is represent the circle. The center is minus g minus f. So what will be that? It is 1 by 2 comma 1 by 2 and the radius is the square root of this. So the radius will be square root of 1 by 2. This is square root of g square plus f square minus c. So let us try to plot that as a graph. So if you can consider this is your 1 by 2 point on x-axis. This is also you have 1 by 2 here. So this is the point where, and the circle which having this much radius is somewhere, you just say that it is something, this circle you will have something like this. I don't know whether it is the perfect shape of a circle, but it is there. But it has to be passing through the point intersection of that one, that is this point, and the image of this point under the map w is equal to 1. This is the point 1 0. Now we need to find out the angle between v equal to 0, that is u-axis, and this circle. So for that I need to calculate what is the slope of this circle at this point. That means a tangent of that circle, that means the tangent of this circle at this point. So to calculate the tangent, we need to take the derivative of this equation, that is u square plus minus v square. So it is 2u plus 2v dv by du. By taking the differentiation of this equation with respect to u, we will have this minus 1 minus dv by du. So this will implies that dv by du will be 1 minus 2u upon 2v minus 1, but at the point we need to calculate at the point this 1 comma 0. So at the point 1 comma 0, that means the value of u is 1, v is 0, which will be 1 minus 2 into 1 upon 2 into 0 minus 1, so that will gives me 1, and the tan inverse of this is nothing but the tan inverse of pi, which will gives you pi will be pi by 4. So that means the angle between its tangent, so if you can consider this is as a tangent here, which making the angle with the positive x-axis is also pi by 4. So here is also we have pi by 4 and here is also we have pi by 4. So that means we can say that this map is angle preserving. Now the next definition says about the isogonal mapping. What is isogonal mapping? Is the mapping which preserves the angle only in the magnitude, not in the sense. So magnitude preservation is there, no sense. That means direction of the angle is not making difference, just magnitude is the same. Then we can say that such mappings are called isogonal mapping. For example, f of z is equal to z0, sorry, f of z is equal to z bar will be the isogonal mapping always, because this will just gives you a mirror image of the curve into the x-axis. So here the angle between two curves preserves in magnitude but not in the direction. So that's why this is known as the isogonal mapping. In fact, if you have the f of z is the conformal map, then f of z bar is always an isogonal map. That you can take it as a note. That also you can try to prove by yourself. Next definition is a critical point. The critical points are those points where the function is not conformal. So a non-zero, non-constant analytic function is in the domain D if f dash of z0 is 0 for some z0 in D, then z0 is called critical point. In other sense, we can say that the function is not conformal at that point. It's called the critical point. For example, if I have the function f of z is equal to z square plus 11. So what are the conformal points of this z square plus 11? So you just need to calculate what is f dash of z, which is 2z. And f dash of z equal to 0 implies that z is equal to 0. Hence z equal to 0 is the critical point. So at this point the function is not conformal. All other points it is conformal. I am giving you exercise to calculate the calculate the critical point of this function, that is e power 2z minus 2iz plus 3. Try to calculate what are the critical points of this by yourself. I would like to give you one more exercise here to discuss, that is determine the image of half plane y equal to x if x is greater than or equal to 0 and x is equal to 1 if y is greater than or equal to 0 under the transformation w equal to z square, and so that f is conformal at z is equal to 1 plus I. So this exercise you can do it yourself. Here you have to show that first of all what are the images of these two half lines and under this transformation w equal to z square, and you have to show that this function is conformal at the point this 1 plus I without using the previous result. That means you no need to use the shortcut for this. You have to do all the calculation for that. Also you can discuss all the elementary functions that we have discussed in the previous videos, that are the identity map, the linear map f of z is equal to az plus b 1 upon z, inversion map We have also discussed the bilinear maps, that is az plus b upon cz plus d, where AD minus BC is equal to non-zero. So for all those maps, you just try to calculate what are the conformal points for this, especially for bilinear transformation, what are possible critical points for this bilinear transformations are there, that you can try to simplify on and do the calculation for that. That is also I am giving you as a homework. So in this video we have discussed about conformal mapping. The conformal mapping means the angle preserving map. So if you have two curves in your z plane, if you transform that two curves into the w plane, if the angle between these two curves remains same, then we can say that the mapping is conformal mapping. We have discussed what are the properties of this conformal mapping, which tells you that the function's derivative is non-zero and the function is analytic, then the function has to be conformal. With the help of that, we have shown the many examples. We have discussed about the isogonal mapping, where the preserving is there but only with the magnitude, not in the form of a sense or a direction. We have discussed about the critical points of those points where the functions is not conformal. So that's it for this video. If you have liked this video, please press the like button. If you have any comment, suggestion or a question, please drop down in the comment box below. Till then, bye bye, sayonara, see you in next video.